This, we're going to dive a little deeper into the least squares regression line that I mentioned yesterday. Okay, and as has been done with most lessons this year, we have a problem that we can use to address the topics that we want to talk about in this level. So the problem here is the school achievement gap between attendance and performance. Okay, so specifically low-income students tend to have lower attendance rates, lower math test scores than middle or upper income peers. Raising this attendance closed the achievement gap where it helped them perform better. So to do this, or to explore this possibility, a random sample of students was collected in Texas. And for each student, data was collected on their attendance rate in terms of the percent of the school days they attended, as well as a raw test score on a state exam, okay, which would be kind of equivalent to a provincial exam for us. So here we see the actual data in a table, and then we see a visual representation of the data in terms of a scatter plot. Given what we talked about yesterday, how would you describe this relationship? Linear, positive, strong, no outliers. Good. Okay. Now, what we want to do with data like this, bivariate data, is we want to make predictions, okay? And in order to make predictions, like I've said in the previous lesson, we want to be able to fit a line, because then if we can get a line, we can get an algebraic equation, which means we can make actual predictions. And then I just briefly mentioned the least squares regression line. Now we're going to talk about a little bit more about how do we actually fit it? Like, what does least squares mean? Okay. But going back to this example, and just to do a little review, what's the explanatory and what's the response? Yeah. Yeah. So explanatory would be the percent attendance, response would be test scores, and how can you tell? How do you know which one is which? We want to know if attendance predicts test scores. And so to make predictions like this, we use a regression line, which you can see the definition there. It describes how the response variable y changes as the explanatory variable x changes, and we use it for prediction. So if we have an equation, and if we know the value of x, we plug it into that equation and calculate the value of y. Okay. So what's the best type of regression line to draw on an equation or on a scatter plot? Well, to figure this out, we have to understand what a residual is. Okay, we're going to talk more about residuals a little bit later on. Okay, but it's the vertical difference between an actual value in the data and the value predicted by the regression line. Those are not going to be necessarily the same. The only way they will be the same is if the data value, the point, fits exactly on the regression line. If it doesn't, there's going to be a little bit of a difference between the two, positive or negative. Okay? So the residual equals the actual y minus the predicted y. Or using notation, y minus y with a little roof over top of it. And we actually refer to this as y hat. So if you are ever asked to describe y hat, like explain what it is, you must use the word predicted. Okay? If you don't use the word predicted, you have not correctly explained what it is. Just keep that in mind. Okay? So, why do we need to know the residuals? Because we use squared residuals to draw a regression line. Okay? Because if we didn't, okay, these are squared residuals, but just ignore the multiplications here and the answers for a second. Just look at the 3 points and the line that's hit on there, okay? If we didn't use squared residuals, if we just calculated the residual, okay, this and this would cancel each other out. This is already the line. The residual, the sum of them would be 0, right? So what if I do this? No, of course, so extreme. Yeah, let's go that way. The sum of those is 0, isn't it? So how can you draw a residual line just by looking at the difference in residuals? Because if you add them all up all the time, they'll always add to 0, no matter what type of line you put on it. Okay, so just the sum of the residuals is not enough, which is why we use squared residuals. So if this is 2 away, for its actual difference, we square it and we get 4. And then for this one, it's -2 away, we square it, we get 4. These are all on, so their differences are 0, and when we square the residuals, we still get 0. Okay? So in model A, you've got 4 plus 0 plus 4 equals 8. I'll erase this. Okay, because we can't make the sum of the squared residuals any smaller. I can't tilt the line any way to make it smaller. This is the smallest sum I can get. In this one, well, this is a perfect regression line because all 3 points are on it. Okay? So you want to fit the regression line around the points so that when you find all the residuals and square them and add them together, it's the smallest sum possible. So like going back to our example of percent attendance and test scores. Yeah.
Would not be 0, 0, 0.
Well, I guess. Sorry, I get a little excited when I talk about square. Yeah, oh, yeah.
Oh, yeah. Oh, it's your back.
So if we look at this one, the way to fit the regression line is such that, okay, this one looks like it's almost right on it. This is pretty small square of the residuals, the distances. So these are the smallest squares we can make to add them together to get the smallest sum. If I tilted this line a little bit, I wouldn't get the smallest sum. I'd get a bigger sum. If I tilted it this way a little bit, I wouldn't get the same smallest sum as this one. This is the best I can do, which is a lot of times why we call it the line of best fit. Okay, so what you need to know about a least squares regression line, or LSRL, it's a line that minimizes the sums of the squared residuals. Not just the residuals, the square residuals. And since it's a line and we want to write an equation for it, we will use a certain type of notation that allows us to find the slope and y-intercept. Unfortunately, in statistics, you think it would be nice if they would just use this throughout everything. Pre-calculus, statistics, but no, we don't. We use slightly different notation and variables in statistical equations of lines. So in regular algebra that you learned like way back in grade 10, to find the equation of a line, x and y represent any point that's on the line, m represents slope, and b represents the y-intercept. With statistical linear regression line, we don't just use x and y, we use x and y hat, which remember means predicted. And the order's a little bit different. Notice that in algebra, b is the y-intercept, but in stats, b is the slope. And there is no a in statistics. There is no a in algebra, but the a in statistics represents the y-intercept. And notice the x, like the slope times the x, goes at the end, where here it goes at the beginning. So just keep this in mind. This is how we're going to do it. Okay? So y hat equals a plus bx, where y hat is the predicted y value, a is the y-intercept, b is the slope, x is whatever the x value is. So going back to our example, if we find the lowest sum of the squared residuals, we will get a line that looks like this. Once we get that line, we can find its equation, and it will be this. Okay? And whenever we write a regression line equation, we always need to state what y hat and x represent. And remember, whenever you state y hat, use this word. Predicted. Okay? Now, you can be asked to locate the slope and describe what it means. Interpret it. Same with the y-intercept. Here is sort of the general sentence you use for describing slope. So for every 1 unit increase in whatever the explanatory variable is, our model predicts an average, whether it goes up if it's positive, goes down if it's negative, in the response variable. So in our example, we would say for every 1 unit increase or for every one, actually, yeah, I'll say that out. For every 1% increase in attendance, our model predicts and then I look at the slope, it's 0.57, predicts, and since it's positive, an increase of 0.57 points in test score. That's how you would interpret the slope. I mean, it doesn't have to be perfectly like that, but you have to talk about how 1 unit increase in the explanatory variable results in a whatever slope increase or decrease in the response variable. For y-intercept, this is sort of the general sentence that you use to explain that. That you should be familiar with y-intercept. It's when x is 0. So when the explanatory variable, which is x, is 0, our model predicts the response variable will be whatever the y-intercept is. Okay. So when percent attendance is 0, our model predicts a test score of what? What's the y-intercept? Yeah. An additional question to be asked, what the y-intercept is, once you interpret it, does it make sense in this situation? Why does it not make sense? Because, yeah, you can't get a negative test score. You can't get below 0. So, I mean, if you have 0 attendance, one would expect 0% attendance. One would expect you to have a really low test score, but not to the point where it's negative. So it doesn't have meaning in this context. So no, because you can't have a negative test score. I mean, if the y-intercept was, say, 2 point something, that would make that would have more meaning. Because then it's not outside the realm of possibility to say, yeah, if you get 0% attendance, you might get something right by luck. No, because you can't have a negative test score. And we actually give that a specific name in stats. We call that an extrapolation. If it has no meaning, it's called an extrapolation. Okay, so that gives you an idea of how we actually get a least squares regression line, how we interpret the information from the equation of a least squares regression line. So just to finish up, making predictions is pretty straightforward. When you're given the least squares regression line equation, you just simply plug in, you got to know whether it's X or Y hat, and then plug it into the proper variable and then calculate it or solve it if it's an equation. So the superintendent of this district asked, going back to our problem, if a student meets our minimum attendance goal, which they've set at 87%, what would their predicted test score be? Well, we would just simply plug that in for X. So we get negative 7.69 plus 0.57 times 87. Is it whole? Not decimals. Yeah, times 87. And if you calculated that, it works out to a test score 41.9 whatever points. Okay. Like I said, you could be given a different type of question at this. You could just say, you know, a predicted test score was 45. What percent attendance would you expect the student to have? Predicted. Okay. I do want to just talk about this discussion briefly. Okay, because there's been really, I mean, we don't really have, and I guess we don't have an issue with attendance here. I mean, if we do, it doesn't seem to affect you guys too much, or most students. Anyway, but there are places where there are real issues with attendance. And there's been a whole bunch of things tried to improve attendance, you know, call programs, hiring attendance case managers, even to the point of using Uber or Lyft to get kids to school, because this is a serious problem in certain neighborhoods, and I'm in Canada and the US and across the world. Okay, so let's say that the attendance does go up. That's that they try something like this, okay, and over time the attendance starts to increase, and then they decide, okay, we're going to do that test score thing again, and yet they get this. The test scores stayed the same. When we thought, well, if we get the kids to school, they're going to learn more, they're going to have more knowledge, and this is going to go up. Why wouldn't it? We kind of talked about this yesterday in the discussion. The idea of a lurking variable. Is there something else that could be causing no increase in the test scores? The kids are getting to school, okay? They're in class more, but they're still not performing well. Yeah.
Is it their ability to study? Like they don't have time to call?
Yeah, maybe, I mean, if you think of high school, maybe some of these students have like work a lot of hours per week because they need to for the family, because they're from a low income family. So maybe these kids are working, they don't have time to study. Yeah, they can get to school, okay, but clearly that's not enough. So that's just one example. You know, there could be other reasons why it doesn't, or why those test scores aren't increasing. You know, maybe they're not getting the support at home that other students are. Who knows? Okay, but clearly there's something else that's lurking. that's causing no increase in test scores, even though the attendance is increasing. Okay.